I'm going to talk about the study group which we organised, V-KEMS organised in January of this year, looking at issues to do with travelling on trains. So the number of people going on trains has massively reduced due to the pandemic. And as we come out of the pandemic and people start to travel on trains, there are going to be issues with infection and so on. And the study group was put together to try to model some of these in advance of when we would actually need to travel on the trains. And to give you some idea of the scale of the meeting, we had 3 experts from the railways: Jonathan Bridgewood from First Group Rail, Ben Ford from Network Rail, and Matt Hunt from the Rail Safety Board, who produced some reports already. And the meeting was facilitated by the KTN, so Matt, who you've just heard from, and Daisy Chapman-Chamberlain. And there were a lot of attendees. And what's nice from this list of attendees is that there's a lovely mix of academics such as myself, industrialists, and lots of very, very good PhD students. And one of the great things about the virtual study groups is that the PhD students have really been enabled to work as fantastic problem solvers to try to deal with some of the issues that COVID has thrown up. And as Matt said, it's been very, very good for their morale and mental health, not only to welcome these problems, but also to find their names on publications coming out as a result. So in most study groups, we try to break down the big problem into sub-problems. So the big problem is how can we reduce the impact of COVID infection on trains? And we identified in advance of the study group 3 sub-problems, which related to 3 different scales of the railway network. So when you go on a train journey, you are going to spend most of your time in a carriage. And presumably that's one area that you can get infected. So scale 1, which was led by William Lee from Huddersfield, looked at controls to reduce the amount of infection that you will get in a carriage. Scale 2 looked then at the journey. So if I'm going to, say, visit my daughter in Scotland, then I have to travel to the station in Bath, get the train to Scotland, and then go off at the other end. And so this group looked at the various issues to do with the whole journey, in particular the business of getting on and off a train and maybe moving through a station on the way. And that group was facilitated by me. And then thirdly, we thought of the big scale. So let's imagine that we have a mass movement of people. So what we were particularly thinking of was students returning to university. Are there ways that we can optimize the network to reduce infection? For example, give students in some universities permission to travel on some days and students in another university permission to travel on another day, so that you don't get massive clogs up to the network, and that then might impact on infection, or in fact be impossible to do given the reduced amount of space you can have in a carriage due to social distancing needed. So those were the 3 scales, and the third scale was led by Jess Enright at Glasgow. So the study group divided up into these 3 scale groups. Each group had, I suppose, about 10 to 20 people in it, facilitated by an academic, but in good study group tradition, much of the exciting and original ideas came from the younger members, especially the PhD students. So what I want to do in this talk is to run you through some of the results that were obtained in these 3 working groups, bearing in mind that this was a short study group. It was only 3 days long. So a lot of what was done during the group has had to be followed up later. And I'll try and talk a bit about what they did during the 3 days, but also where it's going on to next and what that is now leading to. So let's look at scale 1. So this is the carriage level. So the idea here is that you're sitting in a train, presumably on a specified seat, and you are breathing out and you are breathing in, and that there is a risk of infection, mainly due to airflow, also partly due to contact with surfaces. And the Carriage level group was having a study of what the kind of levels of infection might be and how they might be mitigated by controlling the ventilation or the distribution of people in the carriage. So it was looking at things like modeling the airflow, modeling how people interact with the airflow, modeling how people get infected, and how to reduce the infection. Just to give you a bit of context, there is a significantly large body of work going on at the moment under the name of TRACK, which is trying to do what we're looking at in the study group in a lot of detail. This project is being led by Kath Noakes at Leeds and is doing fabulous stuff, but they are throwing an enormous amount of technology at this problem. And what we were trying to do in the virtual study group was see if there might be some simplified models which could complement the work of TRACK to give insight without having to do a huge amount of computational fluid dynamics calculations. So here's a picture I took directly from the report that was written immediately after the study group and was put out as an open access KTM report, thanks mainly due to Matt doing an enormous amount of work to bring everything together. So here are two types of person that can be on a train at any one point, someone that is susceptible to infection and someone that might themselves be infected. Of course, there will be other people that are not susceptible, that have been vaccinated or whatever. And when they're on a train, they're interacting with the air, they're touching surfaces, there's stuff coming in from the outside world, particularly at stations, and the train has a heating, ventilation and air conditioning system which is moving stuff around. And there's a kind of movement of infection between the outside world, between the air and the surfaces, all of which can lead to a susceptible person being infected by an infected person. And the study group considered that one way to model this was to look at the sort of typical airflows. These are Q, these are fluxes between different parts of the train. So you have the inside air in the carriage, the outside air, the ventilation and air conditioning system and surfaces. And the airflow could be described by various fluxes as indicated. And one of the kind of simplified models that can be used to look at a carriage is to make bulk estimates of the sort of flux of air that you might get between these various bits of a carriage and the ventilation system. And from those bulk estimates, you can then go on to get some idea of the infection rate. Now, of course, bulk estimates don't really tell you most of the story. There's all sorts of recirculation and trapping by things like seats and luggage racks and so on. But it's a very, very good place to start in order to get bulk estimates of the infection rate. And then this can be complemented by the much more sophisticated computational fluid dynamics that the TRACK team have been doing. We've left out surfaces here because most of the studies seem to indicate that the primary role of a primary infection route within a carriage is through the air rather than by touching surfaces, because the trains are carefully cleaned and people sit in designated seats by and large. Once you've worked out the flows, then you need to look at how aerosols, people coming from infected people breathing, can move in that. And that can be done by looking at appropriate convection diffusion partial differential equations for how the droplets might move. And here is a calculation that was actually done during the virtual study group, where the flow in the carriage was calculated using a potential flow method, which is a relatively quick piece of computational fluids. There is a person sitting in the carriage, and the yellow is an indication of how the aerosols that that person is breathing out would spread through the carriage. So The study group decided to have a look at different types of person. So some people are very nice, they mask themselves and they're quiet. You might phone, you might talk, or you might be a bad person, remove your mask and phone and talk as well. And all of these lead to different rates of emission of droplets and how they get into the atmosphere. And having done all that, you can then glue them all together into a very famous equation, which is called the Wells-Riley model for infection, which says that the probability of someone being infected is 1 minus the exponential of minus IPQT over Q, where I is the number of people that are infected, T is time, Q is the room ventilation rate. So if you've got high ventilation rate, you're much less likely to be infected. And P and Q are interesting numbers because these depend on the person, essentially how much stuff is being breathed out or breathed in by infected people. And this is quite a well accepted bulk model for how people can be infected, and it gives you a way of assessing the infection risk within a carriage if you can estimate the flow rate, which, as I said, during the study group was done either using simple flow models or bulk flow models. But that was a very useful calculation, and it allowed various types of ventilation to be assessed during the study group quite quickly without having to go to a full computational fluid dynamics calculation. Various assumptions that were made. It assumes that the flow is well mixed. It avoided using complicated CFD, which does require a lot of extra costs. It ignored droplets on surfaces, which, as I said, are those considered not a lesser risk than aerosols. And it also avoided looking at the complicated geometry that you get within a carriage. But still, it gave very useful results, being as a way of assessing how infection depended particularly on the flow rate, particularly on the ventilation, and also on the different types of person within a carriage. I should say that all of these calculations, although they were done for a carriage, could apply equally well to another environment, such as a student in a lecture theatre, and how that depends on ventilation. So here is a few words of wisdom that came out of the group. It became extremely clear that you needed, just to have people normally breathing, that you needed to minimize speech and phone use as much as possible. Even when wearing a mask, when you're speaking or using a phone, that significantly increased the number of aerosols. And on the day when we celebrate Bob Dylan, I'm afraid to say that singing on a train is especially bad and must be avoided at all costs. And bottom right, you can see a graph where the y-axis is the amount of aerosols produced over time, and you can see that singing is really very bad. That's the blue. So if you're on a train, try to avoid singing. Okay, so let's move on to the second scale, which is that of the passenger journey. And let's again imagine that I'm going to visit my daughter in Glasgow. In fact, I won't be visiting my daughter in Glasgow because Glasgow is in level 3 and therefore having to postpone this visit, which is a bit of a shame. But here is a typical journey that someone might undertake, starting from Bath Spa. So you travel to the station, you travel through the station, you then wait on a platform, probably in a crowd, and enter the train from that. You then sit on the train, which is the level 1 problem that we just had a look at. You then, when the train gets to the station, you leave the station and you travel onwards from the station. So here is a typical journey. And when we thought about kind of the various pinch points where infection was most likely to occur, we felt that the worst 2 points were getting on a train where you might be in a crowd on the platform and getting off a train where you're on a queue waiting to get off. And just one immediate conclusion we came to was that the longer the train stays at the station, the better it is. Because if you stay a long time at the station, there's less crush getting on and there's less crush getting off. So that's a very, very simple conclusion that came out of this group, although that is a difficult conclusion for the train operators because it involves changing all their schedules. Okay, so let's talk about getting on a train. So here we are, we're on a crowd on a platform and we need to get on the train. This photograph was taken pre-COVID, so no one's wearing a mask. I actually haven't been on a train myself at all since March 2020, so I have been unable to take photographs of people doing that. So I'd like to talk particularly about the work of the PhD students in my group, led by Simone Appola, who looked at a time model where they assumed that the passengers were entering onto the platform from sort of an entrance or entrances. They'd then mill around on the platform, and then when the train came in, they would then head for various doors. And there are various scenarios that you can have. You can have people with reservations where they know exactly which door to go for, or you could have an unreserved train where people kind of head for the nearest door. And that actually affects the dynamics. And the group considered at the time a model based on a continuum. So you think of the crowd density as being a continuous function of space and time, where there's some advection caused by the intent of the crowd to move in a certain way, and there's some diffusion caused by the kind of random motion within the crowd as you jostle around trying to get to the doors. So this is one way of modeling a crowd. It's quite a commonly used method in the literature, and you can consider various scenarios as people are waiting on the platform. And one of the scenarios considered was that the people would be bunched up in some sort of Gaussian profile in space and time, characterized by an initial spread characterized by numbers β1 and β2. PhD students are amazing. You give them a two-dimensional continuum model with a train with awkward geometry, and the next day they've come back with a solution because they know all sorts of useful software. In this case, the software called Phoenix, and that software allowed them to quickly get a handle on this equation. And in this picture, we can see on the bottom, on each picture, the bottom represents the platform, and the crowd is red where it's densest. And here you can see the crowd moving up towards the doors on the train indicated at the top. And this is where β1 is taken to be 10 to the minus 3. So that's quite a closely spread crowd. Here, sorry, a diffuse crowd. Here we have a much more focused crowd, where I suppose this is a gang that's coming into the platform of people maybe from a football event. So they're all kind of clustered together, moving out into the train. So this allowed us to do some various simulations. These simulations at this stage, we didn't have enough time during the study group to look at the impact of viral load, but still you can get some indication of how likely you are to get infection by looking at the density of the passengers as they go into the doors of the train. And here are various graphs of the density as a factor of the β1, the spreading factor, the density on the platform. So this immediately allows you to get various ideas for how likely people are going to be infected, particularly by the way that they crowd and cluster on the platform. That was as far as we were able to get during the study group itself, but afterwards the ICMS provided a small amount of money, which allowed me to pay for my students to carry on with some extra work on this same problem. And Simone, again, instead of using a PDE model, tried out using an agent-based model where you have different agents interacting. In this case, we have black agents are susceptible people and red agents are infected people. And you can kind of start to simulate the sort of way a crowd might come out from an entrance at the bottom and head towards the doors at the top of the train. And you can build into this simulation different ways of operating. So people can either head for doors at random, or they can go for reservations, and they can enter uniformly or enter in a sort of Gaussian profile. So that's one where people are coming in uniformly. And here is where they're coming in from a kind of entrance where they're more tightly bunched, and then heading off towards the train. And this is work in progress, and we're able to get from this an assessment for how people come into contact, and therefore how likely they are to be infected as a result of getting onto the train. Okay, so once you're on a train, you get to your station and an announcement is made and you have to get off. So we thought we'd better simulate the getting off process. And in a train, when you get off, an announcement is made, you stand up and you're in a queue, and that queue is moving. So an earlier study group that happened last April, we had a good look at queuing in supermarkets as you queue to pay. And this is actually a bad thing. Avoid queues, avoid queues. The problem with a queue is that you may spend quite a long time quite close to someone that's infected. So if you can avoid queues, avoid them. And getting off a train inevitably avoids queuing, unless, of course, the train spends longer at the station, which gives you more time to get off. So we thought we'd better have a look at this, and another one of our students, Tosin Babazola, had a look at the modelling of a queue, and we used a velocity-based model. So the velocity of any particular passenger is based on their perception of the people particularly in front of them, building in social distance. So we looked at this particular model where f was a piecewise linear function, which meant that you wouldn't move if you were closer to a person than the social distance, and if you were in kind of a reasonable distance away, then you would walk at a sort of a constant rate. And based on that, we could then simulate passengers coming off from a train. And so here's a simulation of a 10-person queue coming off from a train. And typically what you have in this environment is what we call a waiting time, so that no one can move because there isn't a safe distance in front of them to move into, and then a moving time. So typically you have a waiting time and then a travel time. And both of these lead to potential viral exposure. So if you're waiting, you're going to be exposed to the viruses of people sitting in the train next to you. And as you move, you'll be exposed to the viruses of the people in the queue itself. And you can see how the waiting time and travel time depend on the number of people in the queue. And then this is work that we're now following up to do more careful calculations of the viral load that you get in that case. Again, this is work which is being funded by ICMS. The final group, headed up by Jess Enright, looked at the rather tricky problem of how you might optimize the entire network. So as I said, the capacity for trains at the moment is much lower than it was pre-COVID, because you have to space people out in carriages, and you desperately want to avoid overloading the system at times when a lot of people might be traveling all at once, such as students returning to university. And another thing you might also want to do, although we didn't consider it during the study group, was how you might want to route the trains so that they don't go through areas of high COVID exposure. So, for example, at the moment, you might want to avoid areas where which are kind of orange on the map, particularly in the northwest, and sadly for me, in Glasgow. That's where my daughter lives. Okay, so this was a problem that was considered by the group. How can we optimize the network so that there are enough trains available, and ask also these sort of fairly thorny questions about whether you, for big events like students returning, you might want to impose restrictions on what students can travel on what days, or who might travel from one part of the country to another. So these are kind of what if, but important questions to ask. So that was considered with the methodology. The group was very, very concerned that this should use a careful amount of data. So they spent most of the time being great train spotters, looking at railway timetables and looking at what capacity there was, and trying to interpret the timetables as well as possible. And from the timetables, that you can then draw up a weighted graph to look at the kind of capacity of different links between different points in the graph. And then that gets informed by the timetable again, and you can draw up a kind of flow diagram. So this is one particular route that was studied in some detail, the journey from Birmingham to Crewe, looking at the flow rate between different stations. So there are about 10 stations on the way, and that gives you kind of some sort of estimated capacity. There's the flow rate on the model, and then this is the optimization question that was then addressed. How can you optimize the fairly limited capacity that you have at the moment with COVID to deal with an expected flow rate, so that the number of trains with the capacity for the carriages can best be adjusted to the flow rate that you have, or equivalently, how can you optimize the flow rate given the sort of capacity that you have? So again,
yes, sorry to interrupt. Are we able to wrap up? For
yeah, I'm virtually there. I've got one more slide to go. So this was the question addressed during the study group, and is still being looked at. And as I say, they are looking at these kind of issues to do with student motion, and this work is also continuing thanks to the ICMS grant. So here is my final slide. These were the overall conclusions of the workshop. At a carriage level, although great work is being done by track, there is still scope for using low dimensional models, and William Lee and his team are following this up at the University of Huddersfield. At the journey level, we're extending the models developed to look much more carefully at viral load, and comparing some of the models that we have with those used by the Rail Safety Board. And at a network level, there's quite a lot of work to be done now in looking at optimizing the network, if it is possible. So it was a great study group. As with all study groups, it generated more questions than it answered. And it's really nice that thanks to the funding from the ICMS, we're having a chance to follow this up and work more carefully with the railway people as a result. And as just a very quick advert, on June the 9th, we're going to have a workshop. This is a joint V-KEMS and Institute of Mathematical Innovation at Bath meeting, looking at transport post-COVID, and everyone is welcome to come to that. So thank you very much, and I will stop.
Thank you very much, Chris. That's an excellent presentation. There's a couple of questions in the Q&A. The first one is from Jeremy. What was the orientation on the diagram of the carriage and the spread? Was that from above or a cross section?
What we were showing was looking down above from a carriage, with the carriage going from left to right.
Okay. A question from David. Have you got enough data to data-driven modelling to complement your and the Leeds CFD approaches?
What we have is a lot of CCTV camera evidence of people's behaviour on platforms. So there's quite a lot of stuff around on that, and that evidence was stuff that we were using. We didn't have time in the study group, but there's also a lot of CCTV evidence of people moving around within a station as well, and that we're using to help calibrate what we've done.
Thanks, Chris. Momin asks, the airflows you mentioned in stage 1, question 1, QN, could they be modelled by differential equations?
Well, the answer is that's what the track people are doing. So most of the modelling in the study group was done using simple block models, because that block flux models, because that's quick and gets you very much into the right ballpark and allows you to use the Wells-Riley equation. But the track people are using differential equation models based upon turbulent Navier-Stokes. The problem is a block model you can do, it takes 5 minutes to get an answer. CFD for something as complicated as train carriage could take days. So that's the playoff between these two different approaches.
Thanks, Chris. There's just 2 more questions now, one from Lewis and one from Kent, and then I think we'll have to move on to Alan. Lewis asks, I imagine these models will apply for similar transport methods, for instance, coach stations, airports.
Very much so. And in the meeting we're having on June the 9th, we have representatives from Bristol Airport and from First Bus. So we'll have a chance to talk about these as
Brilliant.
well.
That sounds hugely relevant, Chris. I guess if people just go on the website, you might, perhaps we can post.
I'll put it in the chat. I'll put a link.
Put it in the chat, and then the participants can find the link to find out more information. And lastly, from Kent, when boarding a train, there are passengers leaving a train. Should your model reflect this? And then walk.
So very, very good question. What we felt was the only safe way of doing anything was to have one door for people coming off and another door for people coming on, because otherwise you get terrible jamming up, and that's terribly bad for anything to do with COVID. So that was one firm recommendation that we made, that there should be exit doors and entrance doors. And the same applies for many other scenarios. So, for example, students going into a lecture theatre is a perfectly good example. So,
thanks very much, Chris.